In this video, we're going to consider some of the formal properties of an orthogonal matrix, and then we'll probably split this into two parts. So then in the next video, we'll relate that to the work that we did in video number 27. This will be video number 28 in our series. The playlist for all the videos is at the website digital-university.org. Okay, the formal definition of an orthogonal matrix is a matrix multiplied by its transpose gives us the identity matrix. Now remember, matrix multiplication is not necessarily commutative, so that a matrix A times a matrix B is not necessarily matrix B times matrix A. But with orthogonal matrices, they are such that we can say they have a left and a right inverse. That is, its transpose, whether it's multiplied on the right-hand side or the left-hand side, it still gives the identity matrix. And the determinant of an orthogonal matrix is plus or minus 1. This is the easiest to show. Let's do this first. Then we're going to look at some of the implications as to what this means up here. Now, the determinant of, say, these together would equal the determinant of the identity matrix, and that's just 1. Well, let's write it like this: the determinant of I, and the determinant of I, of course, is just 1. Now, we can multiply these out individually. That's one of the properties of determinants. So we have the determinant of A times the determinant of A transpose equals 1. Now, for any matrix, doesn't matter what it is, any matrix, say C, and you consider its transpose, the determinant of C, that's equal to the determinant of C transpose. That's one of the fundamental properties of determinants. So, up here then, this is equal to the determinant of A, so we have the determinant of A times the determinant of A equals 1, or we could say the determinant of A squared equals 1, so the determinant of A is going to be plus or minus 1, as we set up here. So that's pretty straightforward to show. Now, what we want to do is consider, this is our formal definition, consider some of the implications of this. So, let's say that we have just a 2 by 2 orthogonal matrix. Say this is matrix A with components A, B, C, D. So that's matrix A, and then A transpose, that would be A, C, B, D. Now, if we take this product of A and A transpose, what will that be? Well, we have A squared plus B squared and then underneath we would have AC plus BD, and then over here we would have AC plus BD, and then down here we will have C squared plus D squared. And that's supposed to be the identity matrix. This is supposed to be 1, 0, 0, 1. So if this is true, this has to be 1. And so does this. And these two are the same, and that has to be 0. So we have AC plus BD must be 0. Well, here's our matrix A. It has a row, let's call it a row vector of components AB. This is a row vector of components CD. And we're saying A squared plus B squared equals 1. So it's a row vector here has magnitude 1. It's a unit vector. CD is also then a row vector of magnitude 1. Now we have AC plus BD equals 0. Well, if we take the inner product, we take the dot product of AB with CD, we have AB. And then when we multiply, when we do the inner product, remember we always take the transpose. So we'd have CD. And this will give us AC plus BD. And we say, oh, that's 0. So what we have then is that the rows are orthonormal. They have, each row vector has unit magnitude, and each row vector is orthogonal to each other. So this is matrix A times its transpose has to equal the identity matrix. So this is telling us then that for an orthogonal matrix, its rows are orthonormal. And we get that from these three equations right here. Now, let's consider this. So now we have A transpose times matrix A, which is this. And that has to be the identity matrix, but let's multiply it out, see what kind of an expression we get. So now we're going to have A squared plus C squared. And then underneath, we're going to have across here and down here, AB plus DC. And then over here, we're going to have, going across and down, AB plus CD again. And then here, we're going to have across and down, B squared plus D squared. And this has to be equal to the identity matrix. So if this is true, A squared plus C squared has to be 1, and so does B squared plus D squared. And then we have AB plus DC equals 0. So we have these three equations. And now, this is matrix A. If we look at its columns and think of them as the components of a vector, we have a column vector with components A, C, and another column vector of components B, D, and we have A squared plus C squared equals 1. So this column vector is a unit vector. So is this one. And if we were to take the dot product or the inner product of these two column vectors, it would be AB plus CD, and we see that equals 0. So this equation tells us that the columns of an orthogonal matrix are orthonormal. They have unit magnitude and they're orthogonal to one another. So together, these two parts of the definition, if you will, of an orthogonal matrix, this tells us that the rows are orthonormal. This tells us that the columns that comprise an orthogonal matrix, they are orthonormal. And again, as we demonstrated just a few moments ago, the determinant of an orthogonal matrix is plus or minus 1. Now, what we're going to do in the next video is remember these equations from the fact that the column vectors are orthonormal. And we're going to relate that to what we did in the previous video, video number 27. Remember, briefly what we did there was we considered a situation, and went over that in some detail in that previous video, where we have a matrix that transforms xy into x prime, y prime. So if we have say a vector here of points x and y, then we could generate a new vector comprised of points x prime, y prime. And that's not the only way to interpret this, though. Again, as we discussed in video number 27 in more detail, x prime equals this matrix times this. That can be the equation for a line. And same thing here, y prime equals a matrix times this. That can be the definition or the equation for a separate line. And again, we went over that in detail in video number 27. The point is that these can be interpreted then as having a single vector r, but expressed in two axis systems, xy and x prime, y prime. That's the two different ways of interpreting this equation, as we talked about in detail in the last video. Then what we also discussed in the last video is that x prime and y prime don't necessarily have to be perpendicular to one another. But if this transforms r into another vector that has the same magnitude, then if we consider the other way of interpreting this, that is where x prime and y prime are a separate axis system, as we had in video number 27, like this, then x prime and y prime must be perpendicular. And again, if this is not making sense, please look at video number 27 when we discuss this in a lot of detail. But here's the question. With what we did right here, what does that have to do with whether these equations generate another vector that has the same magnitude as the original vector here? So in other words, here we have vector r comprised of x and y. We have a matrix equation to give us x prime, y prime, which can comprise the points of a new vector. But remember, as we said in video 27, if this has the same magnitude as this, then if we have an alternative interpretation that these are a new axis, they had to be perpendicular. They must be, that we showed in the last video. But if we have now, we're thinking about in this interpretation, that this here has to have the same magnitude as this vector, what does that have to do with these formal properties of an orthogonal matrix. That is what we'll explain in the next video. So come back for that video. We'll finish up the discussion of the formal properties of an orthogonal matrix, and we'll relate it to what we did in video number 27.